Assalamualaikum and good morning. Today we start our viscous fluid flow MKMM 1313. But before that, we need to go through a few introduction notes of this one. So I think I will go this for very fast because you already need to know. First, in this topic, we will have two type of coordinates. So the common one is the Cartesian coordinates. You already know the Cartesian coordinates, and then we also have problems that are using polar coordinates. So I think you already know these two type of coordinates. So if Cartesian coordinates, so we will have the x, the y, and sometimes we will do the 3D three-dimensional. So we will have another axis which called the z-axis. I think you already know when we talk about the axis here. So we have velocity, the motion of the molecule. So and then, for example, if the molecule is from here move to here, so we could say that it will have the x-axis direction of velocity, component velocity of x-axis, component velocity of y-axis, and at the same time the component velocity for z-axis. So and then you know that velocity is a vector. Then you could use the idea of u square plus v square plus z w plus w square to calculate the resultant velocity. So I think you already know about this idea. So and then the polar coordinates. So you already know that sometimes molecule is not moving linearly, not from one distance to another, from one point to another point. Some situation, the molecule will rotate on the same path again and again. So for example, if we are talking about the tornadoes, we are looking about the vortex later on. So it's not give us distance, but it keep flowing on the same path again and again in a circular direction. So and then for this situation, we will use polar coordinate system. So and then for example, you have one molecule here, so it's rotate on the same trail path here again and again. So we could say that it has the radius axis component, which is the UR, and also the tangent, actually the tangent velocity, which is u theta. So at the same time, for the polar coordinates, we still have the z-axis. So the z-axis is actually normal to this surface. So means that if we have the z-axis is like this, so this is z-axis, so the molecule will rotate here. It will go forward, moving spirally like that. So this is the idea of a polar coordinate with three-dimensional. So again, velocity is a vector. It has magnitude, and at the same time, it has direction. So means that you need to calculate the resultant velocity by using this equation. So and then we will use the Navier-Stokes equation actually to solve problems. So the first thing that you should know is about the conservation of mass and also the conservation of momentum. So we will have these two ideas is very important. So and then if you have time, okay, maybe you could study for conservation of energy. But in this subject, so we not focus on conservation of energy because we not try not to have a temperature parameter here. Okay, because normally when it's involved temperature, it will the medium is gas, because gas is very sensitive on temperature, so it will expand, and then the density and so on will change. So and then a new idea will comes in. So normally for that one, we will you will get in thermodynamics. So we have a master level subject for thermodynamics. So for fluids, so we just we try not to involve any temperature changes actually. Okay, so we go for the conservation of mass, the equation of continuity. So I think this is very simple. You know that from the basic physics law, we found that mass cannot be created. Okay, it's constant. So, but maybe the shape of the mass and so on and so forth is quite different. Maybe you have input as liquid, but the output is in gas, for example. So the physical is different, but the quantity of mass is constant. So the idea, and then the conservation of mass. Okay, this is the basic idea. But in fluid mechanics, we always use the idea of mass flow rate. So mean the conservation of mass flow rate. So because we are talking about fluid, you know, fluid is the moving particle, is the moving element. So everything that's moved, uh, so it's called fluid. So we call have for sure the liquid and the gas is fluid. But sometimes if you do research about molten metal, so with the molten solid, yes, you could use the idea of fluid mechanics to solve the problems. So I think you already know about the Newtonian fluid, non-Newtonian fluid, and then if you see uh, that graph, so you will find the Bingham plastic. So the Bingham plastic is actually the molten solid. Okay, sometimes it's used for plastic, and sometimes it's used for the molten metals. Okay, so this is the basic diagram for the mass flow rate. So I think you already know. We go for the Cartesian coordinate first. So we have the, let's say we have an element here. So let's say we have an element here, so we draw a box here, so and then we assume that the inlet must be equal to the outlet. So and then because we have two direction, let's say we talk about the third dimensional first, and we talk about the two-dimensional first. So means that we need to understand that the inlet here, the inlet for x must be equal to the inlet for y, for the inlet for x must be equal to the outlet of x, and inlet for y must be equal to the outlet of y here. So and then you just, because the mass flow rate, the conservation of mass flow rate is actually the scalar. This, okay, it is not vector, so means that the direction is actually not important. So that's why we have a different direction here, but the way we do the solution is we just add, we just do the summation of inlet here must be equal to the summation of the outlet. Okay, and then you already know, if you look for the unit here, so it will give you mass flow rate, so you will have kilogram per second. So means that the units there is the scalar, so means that the direction is actually not important when we talk about the conservation of mass. So and then so if we solve this one, we could get okay, so this is the first idea of the conservation of mass. So the basic equation that you need to remember is this one. M dot mean mass flow rate, so m dot in minus m dot out is equal to d over dt m element. So means that the mass flow rate for inlet minus mass flow rate at outlet, so it will give us of dm over dt. So dm over dt means the differential changes, the changes of mass over time. So it's still both, all of this equation is still in kilogram per second. So and then, however, why we start with this one? Because we must take care a few situation. So let's say if we have the incompressible flow. So the incompressible flow means that the fluid cannot be compressed. So means that, so the simple idea is liquid. So we cannot compress liquid easily. Okay, if you do some high-end research, you may say that so liquid a little bit can be compressed and so on and so forth. But in common idea, in general idea, we could say that liquid cannot be compressed, so we call it as incompressible flow or incompressible fluid. So the idea for incompressible fluid is we found that whatever go in, so it must equal to the amount that goes out, because the system here is full of that incompressible fluid. So mean if you put 1 liter in inlet, so means that you push another 1 liter at the outlet. So this is the idea of the idea of conservation of mass. So and then for this one, so we found that there are no changes of mass over dt. So here you need to understand that what is the mean of dm dt here. So mean inside this system we found that there are no mass changes, mean increment or decrement of mass in term of time. So mean for t equal 1, for example, at time equal to 1 second, we found that here, okay, the mass is maybe 7 kilogram. So, and then after certain time, for example, t equal 10 second, so we found in this system, the mass is remain 7 kilogram. So that's why we could say that dm over dt is equal to 0. So maybe in this stage, you need to understand the meaning of each symbol, because sometimes you need to reflect the idea of the mathematical symbol from, you need to know how to write mathematical symbol based on the real situation. Okay, because there are no increment or decrement of mass inside the system, so we could write that dm over dt is equal to 0. So then, and then we could bring the mass flow out from the left side to the right side. So we could write, okay, we could write this equation like this one. So, and then, so this is for the incompressible flow. And then let's say we have a system for incompressible flow. So the incompressible flow, we could imagine something like this one. So means that we have the input here, and then we have an output here, but in our system here, the fluid is not fulfill the area. So mean if you give 1 kilogram here in the output, you may have 0 at outlet, because maybe this 1 kilogram is remain in the system and there are no output. So means that we cannot simple write as mass flow rate inlet is equal to mass flow rate outlet. So because the in the situation here, the inlet is not equal to the outlet, so we write like this one. So why it's not equal? Because there are changes of mass inside the system. So how we write the changes of mass? So we write as dm over dt. Okay, some people do like del m over del t. So this is just the partial differential. So it is okay for you to write for dm dt, because we are not particularly see the changes in axis x, y, z. So it is okay. Okay. So and then that's why we could write as m mass flow rate in minus mass flow rate out is equal dm over dt. So and then okay. So and then again, maybe you have compressible flow system like this. You will find that, oh, in this system, all the fluid is full with fluid. The system is full with fluid. But if you talk about the gas here, okay, so normally if you have research about gas, you will have you will use this kind of diagram, because gas is fulfill the space, but it can be compressed. So the previous system like this, it is maybe for liquid. So the liquid cannot be compressed, but you still have an empty space here to give, to make the system can be added. So again, I think you already know how to write this one. It is because we imagine that the system here is compressible. So means that it can be the mass in the system can be uh, in, can be increased or decreased. We could add or deduct the amount of mass inside the system. That's why we add dm dt in the equation, then we rewrite it as this one. So this is the basic idea of mass flow rate. So and then we go back here, just to refresh your idea how to develop the continuity equation. So let's say we go for this, we will use this equation. So, and then we need to calculate about mass flow rate. So mass flow rate can be calculated by using this one, density times velocity and time cross-sectional area. So the equation for m dot is actually to rho, a, and v. So means that rho is density, v is velocity, and a is the cross-sectional area. So here you must very particular, because the area here must be the perpendicular cross-sectional area of the velocity. So means that if you have pipe like this, so it have the incline end like this, and but the velocity will go through straight like this one. Okay, so to calculate the mass flow rate here, you need to calculate the rho, you times the A, you times the V. So because the V is horizontal like this, so the A is actually the cross-sectional of this one. Please do not take the cross-sectional of this inclined area. So this is the very basic idea in Bernoulli equation and so on. So I think you already know about this. So we use this equation to calculate. So we could write as this one. So if you see this equation, you will find that the rho u dy dz is the inlet, the mass flow rate at the inlet here. Okay, so we have the density, which is rho. So and then you know that the x-axis, velocity component is u, and then the cross-sectional area is this times the width here. So it is times dy times dz. So we write as dy over dz. Okay, and then you could make this at home because this is quite a simple one. So you could, so here is the inlet here. So here is the inlet at y, and then this is the outlet for y, for x, and this is outlet for y. For here, yes, this one. And then this is the dm dt, the changes of mass over time. So how to calculate mass? Okay, so the calculate mass, okay, mass flow rate. So we know that normally density is the mass, is the kilogram over second. So means that okay, so this is actually the idea of mass flow rate is rho, a, and v. So and then we could say that here is rho is the density, and dx dy dz is actually the volume. So the idea here is, okay, density dot s. So rho is the density. So density is the kilogram over meter cube. So it is actually mass over volume. So how to get mass? So we could calculate mass is equal to rho times volume. So the V here is volume, not velocity. So that's why to calculate the value of m here, so we multiply the value of rho here and the value of dx, dy, dz, which is the volume of this one. So and then we have the parameter t here to give the mass flow rate. So and then if you do that, okay, you will have this expression. So and then please make sure that you know to do the partial differential. So if you do the partial differentials, so you could expand it like this one. So and then you could simplify it to become this one. So and then if you do the calculation only for two-dimensional coordinates, so you could neglect the value of z-axis there, and this is the continuity equation for Cartesian coordinate. So this is the basic idea. What you need to do is just do this at home and try to get the ideas how it can be simplified. So and then we go for the Cartesian coordinate. Okay, so this is the simple notes for the continuity equation. So it is okay for you to remember the final terms of this continuity equation, because sometimes it is no need for you to do the derivation. But as a master student, I hope you could do that, the derivation of this continuity equation.